Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
3, 2, 1, go. All three are dropping now. The two balls are falling at pretty much exactly the same speed. And the feather is only about an inch down from the actual platform, just as the other balls are about to collide with the ground. So the feather is still coming down, the balls are already kind of bouncing back up. Well, essentially, the feather, you can see it being pretty intricate and fluffy there, experiences a lot of air resistance. Then if we remove the air, in theory, the feather should fall at the same rate as this heavy, massive ball. Okay, so we need to reset up the experiment. So we'll put the balls back inside the chamber. It's now evacuating the chamber through this line here, so it's sucking out all of the air. So this is our gauge up here that tells us what pressure we have. This is reading 1,000 millibar, so that means that we're at atmospheric pressure at the moment. So we should see this number come down. There, it's coming down. Now that it's coming down, it comes down fast. Okay, so we're all ready. The chamber's at very low pressure now. There's very, very little air in there now. It's like almost a factor of 1,000,000 kind of down in pressure. All right, so now we're going to drop it in vacuum and see what happens.
Are you ready?
Are you ready?
I am recording.
Okay, I'm now driving it out. Ooh, and there it went. And the feather's falling exactly the same speed. The big ball is slightly behind. I guess that fell off slightly later. But yeah, they're falling exactly the same speed. It works. Okay, so here we haven't got any air in the chamber. So unlike kind of in the normal world where we're surrounded by air and we see everything fall at different rates and may attribute that to like maybe heavier things having a greater gravity or a greater acceleration to them, fundamentally here, because we can actually see that the air is what's actually causing the feather to fall slower. The acceleration due to gravity is a constant.
Okay, there we are. So we're fully loaded. Here's the first one. We've got the marble on this side and we've got the feather on this side. I hope it doesn't get caught. I've had a few outtakes where it keeps getting caught on the hinge. But basically you can see it's dead simple. I just pull these neodymium magnets, which are really strong magnets, off, and it just drops it. So I'm just going to show you this first one. Now this is with the air still in the chamber. So we've not removed it yet, we've not pumped it out. See what happens, I'm sure you can predict what's going to happen. 3, 2, 1. There you go, so that was quite noticeable there. The feather obviously fell slower because the air's getting trapped inside it. So now we're going to try it with a vacuum. So I'm going to pause it and just reset up. And you might hear the noise of the pump when it comes on, it's very noisy. So just hang on. Okay, so the pump's whizzing away here. This is sucking all the air out of the jar. As you can see here, if I lift it, we've got a good suction there. I'll hear the noise of the pump change in a second, which will tell me that it's just changing now, which will tell me that it's got a good vacuum. And it's pretty much reached the maximum vacuum. You see the ball moving, which is quite strange. So I'm going to turn it off now and see if we've got a good vacuum to try this experiment. Alright, so hopefully, well, I'll tell you what, you make a prediction before I do it. So there's no air in there now, and let's see if you're correct with your prediction. 3, 2, 1. There you go. So I hope you predicted it correct. As you can see, they both hit the ground at the same time, which is what happens with falling objects in gravity field if there's no air, because gravity, believe it or not, is the same on this object as it is on this object.
As you can see, the feather falls slower than the coin does. This is because the feather and the coin are falling through air, and air is made up of stuff. And this stuff pushes up on the feather and the coin. This is what we call air resistance. Now, air resistance has two factors. One, the mass of the object, and two, the surface area of the object. So our feather is very light. It has a small mass, but a very large surface area. So that means it falls slower due to air resistance than the coin does. So now we've removed all the air from the tube and we've eliminated the air resistance. Now our coin and our feather will fall at the same speed. Galileo was right.
Okay, today to test out my new slow motion camera I got, I'm going to be dropping a feather and a chunk of metal and see if they hit the ground at the same time under a vacuum.
Yes, science!
So the key to this experiment is dropping them at the same time. So what I'm going to do is I'm going to attach the feather to the top of the vacuum chamber with a magnet. So this experiment proves that gravity pulls on everything with the same acceleration. And the reason is because the force that gravity pulls down on you is proportional to the amount of mass in the object. So the more mass an object has, the harder gravity pulls on it, but the more mass it has, the harder it is to move. So what that amounts to is everything is pulled down at the same acceleration due to gravity. But what makes it a little bit messy is that in air, there's also air resistance when things fall, and so you can't really see how everything falls at the same rate. But if you remove that air, then you should be able to see that effect. Okay, first we'll do in-air test. So this is dropping a feather in air. Okay, we're under full vacuum now, so let's do our test under vacuum and see if it looks any different. Okay, I want to do it in normal speed so you can appreciate how fast the feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1. Looks like it almost gets pushed down. It's weird to see it fall like that.
Well, if you drop a feather and a bowling ball in a vacuum, they'll fall at the same rate. You think you've seen it all in this job, and then something like that comes along.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and It does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. The feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
Do it.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
4. Cameras on. 2. 1. Release.
Search your feelings, you know it to be true.
If the Earth is spinning at one rotation every 24 hours, that means that every hour it has to turn 15 degrees. And if the gyroscope is mounted anywhere on Earth, it's going to drift. In today's 21st century navigation systems, they're using what's called a ring laser gyroscope. It is extremely precise.
Yes, science!
If we could simply get one of these ring laser gyroscopes, we would be able to prove once and for all that there is no rotation to the Earth. One of the people in the community actually purchased one for $20,000. But what we found is when we turned on that gyroscope, we found that we were picking up a drift. a 15-degree-per-hour drift. Now, obviously we were taken aback by that. Wow, that's kind of a problem, right?